All right, so over the last several slides, we talked about different factors in the SN2 reaction that affect the rate of the reaction. Now, just because we don't have the ideal conditions for the SN2 reaction, it doesn't mean that we can't get a substitution reaction to occur. It just means that it's unlikely that we'll do an SN2 reaction. So there is a competing mechanism called the SN1 mechanism. So very often the opposite conditions of the ideal SN2 reaction will lead to an SN1 reaction. So here's an example where we have a tertiary alkyl halide reacting with water. Water will serve the role of both being the solvent and the nucleophile. So as we discussed previously, um, tertiary alkyl halides are very poor electrophiles for the SN2 reaction. Water it makes for a very poor solvent for the SN2 reaction because it's protic, and it also makes for a poor nucleophile because it's neutral. So we have three different reasons why we don't want to combine these two if we're trying to do an SN2 reaction. However, we still get a substitution reaction, and you can see by the products that the water, the OH group, has replaced the bromine in the products. We do get a mix of two different products, one that has inversion of stereochemistry, so the OH is facing on the opposite side of the molecule as the bromine did here. And we also get retention of stereochemistry in one of the two products. So this OH is on the same side as the bromine, so we call this the retention product. So this reaction is a SN1 reaction, or it occurs through an SN1 mechanism. And SN1 reactions in general have a rate equation or rate law equation that has the rate being equal to a constant K times the concentration of the alkyl halide raised to the 1 power, although it's not shown here. Notice missing from this equation is the concentration of the nucleophile, which we saw in the SN2 reaction. So it turns out the solvent, or the nucleophile in this case, does not really play a role in how fast the reaction occurs. So we can have a bunch of the nucleophile and it wouldn't change the rate of the reaction. However, the alkyl halide will affect the rate and it affects it directly. So as we double the concentration of the alkyl halide, we will double the rate of the equation. All right, so let's talk about the mechanism for the SN1 reaction. So you might recall that SN2 reaction occurred in one step. The nucleophile attacks from the backside. So water, let's say, was the nucleophile, would attack from the backside of the leaving group, and you would get the products from it. In the SN1 reaction, however, everything occurs in two steps. So first, the bromide leaves, forming a carbocation on the carbon that contain the bond to the bromine. Then water, or whatever nucleophile we have in the reaction, would attack that positive charge, that carbocation, to form essentially the product. Now, due to the fact that we need to remove one of these hydrogens, there is a third step shown here. So another water molecule could remove this hydrogen to form a neutral product. So one of the things you might notice is this sort of key intermediate in this reaction, this carbocation. Carbocations, to remind you, are trigonoplanar. So basically, these three methyl groups are on the same plane, and they form a flat surface around the carbocation. So the nucleophile, it is just as likely to attack from the top side as the bottom side. So there's basically a 50-50 chance it will attack from the top or bottom. That explains why in SN1 reactions we get roughly about 50% of the product being the inversion of stereochemistry, and then the other product which occurs roughly in 50% is the retention product. And so again, that is due to the fact that the trigonoplanar stereochemistry of the carbocation allows for attack equally on both sides of that carbocation. All right, so here's another look at that carbocation. We could start with the structure in the middle. Here's our carbocation. It is trigonoplanar, and basically it's as flat as can be. So the nucleophile, it is just as likely to attack from this side as it is from this side. That would lead to inversion of stereochemistry on one side or retention on the other side. And it occurs roughly in 50-50 by a 50-50 chance. Now, in some cases, the SN1 reaction will lead to a slight excess of the inversion product. We can explain that by the fact that the leaving group, as it leaves and forms the carbocation, it's sort of blocking one side of the molecule. So it is slightly more likely that the nucleophile, in this case water, would attack slightly more from the opposite side. And so in this particular example, we see about 60% inversion compared to 40% retention, where the OH attacks from the same side as the leaving group.